Our first talk in this session is an invited presentation by Katja Poppenhaeger from Queen's University Belfast on how planets affect cool stars. This is a 25-minute talk with 10 minutes for questions. Thank you.
Great, thank you. All right, mic is working, wonderful. So first of all, I would very much like to thank the organizers for inviting me back here. It's my first time being back here in the Boston area in the past 3 years, and I am enjoying this meeting immensely. So, what am I going to talk about here? I will talk about how planets affect cool stars. And this is to be understood in the relation to the talks that we've heard earlier this morning, where we learned a lot about how stars sculpt the space weather in which potential exoplanets are embedded. Now, this talk is basically talking about things the other way around. What might actually happen to our exoplanet host star due to the presence of the planet around it? So, let's see, I have 2 clickers here, clicker and a pointer. This will work. So, what I'm going to show you here and what I'll be talking about for most of my talk are systems where we have a host star and an exoplanet in a close orbit. And this thing that I'm actually showing here, this is one exoplanet system drawn to scale. This is actually the WASP-12 system. We have a G-type host star, and the sizes of the objects and this distance is actually drawn to scale. So we have basically a Jupiter-sized planet orbiting within a few stellar radii around that host star. It's a fairly close system, actually, that we have here. Now, what are the potential things that we might be talking about here? Does this? Oh, I should be doing this. Let's see. So this is what I want. Okay. So when we are talking about exoplanet host stars, we are mainly talking about cool stars, which is very fitting for this meeting, obviously, here. Although we think that this is also an effect of where we are able to detect exoplanets with relative ease given the exoplanet detection methods that we have. So there are a few posters out there, for example, about exoplanets around more massive stars. But given that I'll be talking about these star-planet interactions, this is indeed our favorite type of star that I'll be talking about, namely cool stars. And these systems that are relevant for this topic here basically have massive exoplanets, so typically Jupiter-sized things, maybe a bit smaller things from time to time, that are in few days orbital periods around their host stars. Now, here's another thing drawn to scale. Basically what I've done here is I've put a white light image of the solar corona here under the star. And actually, when we look at these very close distances, we can actually see that the exoplanets, some of these systems at least, are orbiting their host stars within basically the extended coronal structures here. So we should expect some intriguing effects here if we indeed do have sensitivities that allow us to study potential effects that the planet might cause. Now, what are the actual things that we might expect to see in such systems? So one of them, and this is a pretty straightforward one, is gravitational tidal interaction between the host star and the exoplanet here. So these 2 objects here will raise tides on the surface of the other object. And we can, I will go into this in a bit more detail, we can expect certain things to happen here. For example, we can expect, if this thing is in a very fast orbit and the host star is rotating not quite so fast at the moment, we can expect some effects on the stellar spin. And as we have heard in many, many talks already at this meeting, the stellar spin causes a lot of things to change, basically the magnetic activity level and all sorts of observables that are associated with that. Another thing that we might want to think about are potential magnetic interaction effects. So we of course do know that our cool stars have magnetic fields, and I'm just showing here the dipolar field. Usually stuff is much more interesting when we have magnetic structures here on the surface, but just for this little cartoon, I put this one here. And as we know from our own solar system, the massive planets typically also have quite substantial magnetic fields, actually. So when we have these objects in close proximity, we might expect that there's some interaction happening between the magnetic field structures that we have here. And finally, what I'll be very quickly talking about at the end of my talk is Okay, I'm quickly showing you this picture, of course. So these are the more interesting things that we have here on the surface. So we might expect something to happen with the stellar flares or with the hotspots here, which are the actual magnetically governed features on the stellar surface. The final thing that I would like to talk about towards the end of my talk is what sort of things will be happening to the exoplanets if we have heightened, say, magnetic activity, heightened flare rates or stuff like that. So we might expect things like atmospheric blow-off to happen for these exoplanets here. And I'll be talking a little bit about the potential feedback effects that we might expect when having a nearby planet sitting there that might be doing stuff to its star, which in fact, again, governs what is happening to all the exoplanets in that specific system. So what I'll start with is the tidal interaction here. So let's say we have here a host star of a planet. I'm going to go to a slightly different picture for this one here. Oh, sorry, this is very slow in reacting to something. There we go. All right, so let's go to a slightly different picture here. So let's say this is our host star here, okay, this is our exoplanet here. And what we typically observe when we don't have a particularly young system, if we have a moderately old system, right? We have a cool star here that is rotating with a rotation period of, say, 10, 20, 30 days, something like that. And if we have an exoplanet in a very close-in orbit, we typically have orbital periods of just a few days duration. So what happens in such a system is that the exoplanet raises a tidal bulge on the host star, and since the exoplanet is moving faster on its orbit than the stellar spin, that tidal bulge will lag behind with respect to the subplanetary point, which means that the exoplanet can gravitationally pull on this bulge and we have a tidal torque. And what this means over longer periods is that we can transfer angular momentum from the planetary orbit into the stellar spin. So we have basically an exoplanet that slowly spirals into the star over time while the star spins up over time. This is actually a thing that we know exists. We know, for example, that it exists from the Earth-Moon system, where we have this effect working into the other direction. So we have the Earth spinning quite quickly and the Moon rotating around quite slowly, and we actually do observe the angular momentum transfer the other way, where the Moon is moving away from the Earth very slowly, and this is observable. Okay, but back to these kinds of systems. What does this mean? It means two things, right? It means we can spin up a star and we will have planetary orbit losing angular momentum. So we will have planets spiraling into the star, and how quickly that happens basically depends on something called the tidal quality factor, which is something that we can't measure very well. But we do know, of course, that we observe hot Jupiters out there. So they're still there. They can't all be suddenly gone. So we can make some constraints to the lifetimes of exoplanets that are tidally interacting with their planets. There were a few initial studies that set the field for this a little bit. But this is something that is still quite a bit under debate, what these tidal quality factors are actually. Now, what does this mean on the stellar side, right? Let's say we really want to test for how our star might be spun up by the planet. This is, of course, a bit of a tricky business. Otherwise, this would have been settled very long ago with observations. But what stars, of course, do on the main sequence, we have seen quite a few talks about this already. They are spinning quickly in the beginning, having intense magnetic activity, which I measure here, for example, with the stellar X-ray luminosity. Then over time, we have loss of angular momentum for this star through the stellar wind. It magnetically breaks, becomes slower rotating, and the activity goes down. So we have a rough idea, if we know the stellar age, we have a rough idea what the approximate rotation period with a certain spread and the activity level with a certain spread should be. And so if we have planet-induced effects, if we get planets that cause stars to spin faster and be more active, we can try and test for this. And some of the earlier studies actually try to do something like this. There's a lot of stuff going on in this plot, but basically people initially took the whole exoplanet zoo as it was known at the time and tried to sort these systems by how hot Jupiter-like are these things. So here are the things that are close in and fairly massive, and these are the things where we have far out planets that are not so massive, and then sort them here plot their activity levels and search for some trends. And this initial study by Vinay Kashyap, which had quite a few upper limits, but still there was a mild trend for things that are hot Jupiter-like to have slightly more active planets amongst all that scatter. So that's quite interesting, but of course we have to think about what might be causing such a trend, and there was a lot of discussion also within the original paper already. And the thing that we mostly have to think about when we try to do it this way for a large sample is the following. How easy is it to detect planets around certain stars, right? So if we're here in the area where stars have low activity, basically, I'm putting this here in quotes, but small and large planets are relatively easy to detect. However, when we go to the really active stars, planet detection becomes much more difficult. So in this regime here, only things that are roughly like hot Jupiters or maybe hot Saturns or so are still relatively easy to detect. So what we get in such a plot just from our planet detection methods is something that roughly scales into some direction. This stuff we can detect quite easily, and this stuff here, we have a skew in there already that doesn't necessarily have anything to do with effects from the planet on the star. So we need to find some other way to look at this instead of just taking a large sample and trying to run with that. Here we go. So if we have, let's say we could actually find out if a specific star, one specific star is overactive or over-rotating, we need to figure out if this is some form of planetary influence or just the natural state of the star because it's a little bit younger. We've heard from a lot of people already that pinpointing the age can be quite difficult, right? But if I have a reasonable age estimate somewhere, then I can see, am I within what's reasonable here or am I far above that level? And a few reports for some overspinning or overactive stars have been reported where we have reasonable ages from isochrones where things seem to be quite quickly rotating. This one here as well. Here at this meeting we saw the overactivity of HAPI 11. So there are a few things, a few reports that this might be something that's going on. Now I'm going to show you some of my work, how I decided to tackle this problem. What I try to do with this problem is I was using planet hosting wide binaries. So where we have a star, one of them hosts a planet, and there's another companion star, common proper motion star usually, that has the same age. And then we can test if the star with the hot Jupiter tends to be overactive compared to that same age star. And even though maybe we can't pinpoint the whole age of the system very accurately, we would at least expect for these things to have the same age, even though we don't know it exactly. So here are a few of these systems here, and I have chosen X-ray activity as my measurement for the magnetic activity of these planet-hosting stars and their companions. And yes, we can measure the X-ray luminosities of these things, and we can also sort of sort things into systems where the exoplanet and the star should be strongly tidally interacting or very weakly tidally interacting, depending on the mass of planet and star and their distance. Now, how I do this, I'll quickly walk you through this. So this is, again, how the X-ray luminosity of stars behaves over time for different stellar mass bands here. And in a weakly interacting system, when we're looking at the star without a known planet, we find a very low X-ray luminosity for this one. So probably this is a relatively old system, even though we can't maybe pinpoint it given the scatter that these relations typically have. So for the planet-hosting star, which in this case tends to be a bit more massive, we would the activity expect to be somewhere here. And indeed here, when we measure it, it is maybe a tiny bit higher than what would ideally be expected for the range of stars here in that age range, but it's basically consistent with what we expect. However, going to systems where we expect strong tidal interaction between the planet and the host star, these are again the stellar companions that don't have any known exoplanets. Again, low activity, probably old age. These stars, again here, these are much higher in this diagram than what we would typically expect for same-age stars. They are actually quite far above the typical range what we would observe for these kinds of stars. And so if I all put this together here, so if here sort things that are strongly tidally interacting, and these are the ones that are weakly tidally interacting, we typically find an overactivity of stars here in this regime, and either similar activity or even a bit under activity here for things that are weakly tidally interacting. So this is, I think, a very intriguing hint that we can actually observe a tidal effect on the activity of stars in systems with hot Jupiters. And to summarize this one here, when we want to study something like this, we need to be careful with how we select our samples. The detectability of exoplanets is related to the activity level intrinsically. So we need to compare this to some reasonably chosen expectation through a stellar age, or maybe a stellar companion. What I now want to cover is the magnetic interaction here. And this is something that's very intriguing because we're very much interested in magnetic structures on stars. Something to consider here, the simulations that some people have done, for example, Rakesh Yadav here, we expect quite strong magnetic fields for some strongly irradiated hot Jupiters. They can be actually fairly high dipolar fields here, much stronger than we see for Jupiter. So we might actually expect some interesting effects like flare triggering or something like that going on. Of course, the seminal discovery paper here by Evgenia Shkolnik found modulation of the calcium-2 activity of the host star in phase with the planetary orbit, like a hot spot in the chromosphere being dragged around, which is quite interesting here for 2 out of a sample of systems. On the other hand, there's also absence of magnetic effects for here a very close star-planet system that has no X-ray activity at all, or switching of magnetic activity modulation just to the stellar rotation period. So this stuff is a bit tricky. Other things that are very intriguing that have been reported relate to something either planetary or coronal rain. So this is some interesting system here, hot Jupiter system, and work by Ignazio Piliteri, where repeated stellar flares were observed, not after the transit of the planet, but after the eclipse of the planet, so when the planet is behind. And the idea was here that maybe as the planet comes around, and we can start to see it again, we see some material here evaporating from the planet falling onto the host star. It's interesting stuff. Other things that have been reported recently are UV variations in line fluxes in one half of the line, basically, not in others, that occur around the transit of exoplanets, which were interpreted as mild hints for something like planet-triggered coronal rain. So this is all really interesting stuff. But what I want to point out with these things is that we have to be very careful because stars are, of course, stochastically flaring objects. We can find a lot of interesting things that change over time, but if we don't have a really, really large data set, it's sometimes hard to tell if this is a planetary effect or if we are just a tiny bit lucky to see things reoccurring at a certain phase that the star would have done anyway, also without a planet. One thing that I find very exciting is actually the concept of studying planets in an eccentric orbit. So something that has been observed for stars, stellar binaries in eccentric orbits, is that flares may be triggered by colliding magnetospheres as these two objects approach each other. And something similar might also be happening when we have a planet going around as it comes in here and wiggles some magnetic fields around, right? We could imagine something like that to happen. And some very exciting observations were done by Antonio Maggio and co-workers. So these are X-ray observations of one such eccentric system. Now, this thing is not the object of interest. This is just a thing that happens to be close on the sky. This little box here is where our star should be. And when the planet is far away, no X-ray emission is detected at a detectable level with XMN. But when the planet is close to the star, actually in these two epochs here, the star is actually detected in X-rays at higher luminosity. And this is quite intriguing because this is a system where we do have an expectation when stuff should happen, and it actually happens at this point in time which is basically the only time where we can physically reasonably expect a planetary influence to occur. So I find this very interesting because it's a more constrained system in terms of our expectations for star-planet interactions. So, yes, exactly. So here's the cartoon again. We might expect something like flare triggering here. Now, for people interested in exoplanets, this is, of course, not only cool because we can do something to the star, but this should also somehow depend on the planet's magnetosphere. So it might be possible if we can find more objects like this and consistently detect something like this, that we get a handle on estimating how many of these stars have strong magnetic fields at all when they are able to do these kinds of flare triggering things. Now I want to talk a little bit about what this actually means for the exoplanets. So we have seen a few things where we can expect stellar magnetic activity to be increased if we have a hot Jupiter, and maybe some intriguing hints that there's also episodic changes when the Jupiter goes around. What does that mean for the exoplanets, any exoplanets in such a system? So the way we study potential mass loss is basically through transits again. So usually what we can do with the exoplanets when we have the viewing geometry right, we measure the transit depth of that thing, and that gives us a measurement of the stellar radius, the planetary radius squared over the stellar radius squared. So if we go to different wavelengths, this stuff changes. Basically, we can do a spectroscopy of exoplanetary atmospheres here. So what I'm showing here is the transmissivity of the Earth's atmosphere. And of course, optical stuff reaches the ground. And if we go to the infrared, photons basically have a much shorter distance they can travel through the Earth's atmosphere. So if we did a transit detection experiment with the Earth, we would see a deeper transit at certain wavelengths here in the infrared. And similarly, at short wavelengths in X-ray and in the ultraviolet, which is typically used for these evaporation experiments for exoplanets, we should see a much deeper transit because these photons are absorbed high up in the atmosphere, which effectively increases the planetary radius. So actually, Earth's radius is about 100 kilometers larger in X-rays than it is in the optical. So what does this look like? This is a fantastic result. This was a really exciting one by Jennifer Kulau, and later also published by Ehrenreich and collaborators. So I'll walk you through this plot a little bit. It's a bit hard to see, but this is basically the time axis, and we see the optical transit of the planet as this dashed black line. It's a hot Neptune, so it's a very shallow transit here, right? Observing this in the hydrogen Lyman alpha line in the ultraviolet, the blue and red are the blue and red wings of the line, there's a much, much larger signature of this thing. This is basically almost half of the star is occulted in Lyman alpha, which is super exciting. This is a huge signature, trailing in time a little bit after the actual optical transit. And this has been interpreted as a big comet-like tail that is being blown off that exoplanet. And this is really exciting, right? Because this stuff, of course, means that the planet loses quite a bit of mass. And this informs our habitability considerations, for example. Other things that we can study is we can also try to do something similar on X-rays and look for deeper X-ray transits of exoplanets, which tells us something where different kinds of photons are absorbed. So this stuff here basically traces hydrogen. This is hydrogen Lyman alpha line. In soft X-rays, we actually see, we actually see absorption by metals, so carbon, neon, oxygen, that kind of stuff here. So we can use this to trace different atomic species in the exoplanetary atmosphere. Now, over time, this becomes very interesting because, of course, our stars, no matter if we have star-planet interaction or not, in the beginning, stars are way more active and then they decrease in their activity. And so we have strong atmospheric erosion of these planets in the beginning and much less so as the star becomes older. The typical mass loss, if we integrate that over a typical lifetime, say 10 gigayears or something like that, is fairly small for Jupiter-like things, but can be very substantial for Neptune-like things or even smaller things. So we might even erode the whole atmosphere and be left with a barren rock after some time. And this is some really nice work by Eric Lopez looking at how different exoplanets in the same system might lose different amounts of their initial hydrogen-helium envelope. Interestingly, this is some recent work by my PhD student Rachel Booth. We can study how the X-ray activity of these stars actually behaves at old ages. So people are doing a tremendously great job with looking at clusters and so on, where we have a lot of stars of a given age and can study the spread and so on. And usually this gets quite difficult at older ages because we don't have that many clusters that are really old and nearby enough that we can actually study the X-ray emissions. And so what Rachel has done here is actually she looked at stars, individual stars with astroseismically determined ages in the solar neighborhood and got their X-ray flux. And interestingly found that this decay of the X-ray activity becomes much, much steeper at these old ages. So in generally, this might be very good news for habitability because we lose quite some atmosphere of exoplanets here, but once we enter these ages, whatever is left of atmospheres might be surviving for quite a long time. And coming back to the star-planet interactions, if we have a system where there's a hot Jupiter and there is actually a stellar spin-up, an increase in magnetic activity, for that particular system, this evolution might not necessarily look like this, but it might actually look like something like this, because we have a continuous input of angular momentum from the planetary orbit into the stellar spin. So for some of these systems, this evolution here might be altered, and this of course has consequences for all exoplanets that might be present in that system and their atmospheres. So with this, I'd like to summarize a little bit here. What do we know and what can we at the moment study in terms of effects that planets can have on their host stars? For the tidal interaction, this is actually measurable when we have some form of stellar age proxy, or at least have some idea, some comparison, some same age comparison that we can work with so that we can compare the activity levels. For magnetic types of interaction where we need to detect some episodic things, right? We need to be very careful, actually, right? Because we have stochastic activity going on anyway. So we need very good orbital phase coverage, either that, or we need a good model for our expectations when stuff should happen, so that we don't need huge timelines of observations here. But this is tricky stuff to sort out because we don't even quite understand when stellar flares should, normally occur when the planet is not doing something to it. In terms of any feedback effects and the planetary effects, we have seen already in the exoplanetary community that mass loss from close-in exoplanets is actually quite common from what we can observe. And there are potential feedback effects in these systems where we have a hot Jupiter plus something else where we might be interested in the habitability. So this is a very interesting field to study at the moment. And with this, I would like to plug in some shameless self-advertising because I am actually hiring. In a couple of months from now, I'll be moving to the AIP, the Leibniz Institute for Astrophysics in Potsdam, and starting a group there. And if you don't know where Potsdam is in Germany, this beautiful little binary-like system is Potsdam, the slightly more massless object, and then there's Berlin here as a slightly bigger star. And I'm looking for PhD students and postdocs to join my group. So if you might be interested, find me here at the conference and come and talk to me. And with this, I'm happy to take questions. Thank you.
Thank you. Okay, floor is open for questions.
Jill Sager from Boston University. I was just wondering, if you consider the magnetic effect of multiple planets around a star, would you expect those magnetic effects to be additive? What are your thoughts on that?
Okay, that's a really interesting question. Okay, so the systems that I usually study have one hot Jupiter going around, and we only study the innermost planet, basically, because that's, observationally, that's complicated enough and trying to sort that out. But it is actually a relevant question, because we have some systems where the innermost planet is not the most massive one, and then comes slightly farther out, comes a more massive one, right? And at the moment, observationally, it's not clear at all which one might be doing more. I think it's very interesting to study, and if one can get observations with very good cadence, where one could actually try and sort out stuff that might be happening at two different orbital periods. I think that would be very worthwhile to exactly figure out if it's mostly mass that causes the effect or just proximity, for example.
We have a question. I'm sorry, was there one over here? Yes, just a gentleman. Sorry, I'm very confused. We'll get to you.
Hi there, James Doherty from the Open University. The team that I'm working with at the OU has done a lot of work in this area as well, and have looked at mass loss from the WASP-12 system, and have seen kind of decreased activity levels, which we've hypothesized is due to mass being stripped off the close-in planet, and then absorbing some of the emission lines in the calcium H and K lines. So that's reduced activity, which has been observed in that system, but equally you could see reduced activity due to star-planet interactions, as you flagged up in the WASP-18 example. How do you think you might distinguish between those two scenarios?
This is tricky, right? This is hard stuff. I was very intrigued actually when a few papers about decreased activity came out. So this was generally a few years ago, because we were all looking for the increased activity. Then all of a sudden you see something going to the other direction, and you're wondering, are we probing the right model, or what is going on here? I think something that one might try is really going for extremely multi-wavelength with these kinds of things, because certainly with your group you have certain expectations where the evaporated planetary material should be absorbing and at which temperatures there shouldn't be an absorption effect. I know that these data sets are really, really hard to get, but I think it would be very worthwhile if one could get them to compare at different, basically, line formation temperatures to see what's actually going on.
Cool, thank you.
Thanks. We have a couple up front, and then we'll get some in the back.
Rachel Austin, Space Telescope. That was a nice talk. I had a question for you. For the close-in planets, can you use those potentially as probes of the stellar wind and get some independent constraints?
Okay, so this is not something I personally do a lot, but I know some people are thinking about auroral emissions from close-in planets, where you would actually expect some stellar wind. I mean, you need some stellar wind to make that happen. That's not something that I personally do a lot, but my impression is that that's at the moment quite a stretch to get that into an observable range with the current telescopes.
Hi, Celia Damiani from Max Planck Institute of Solar System Research. So you measured the activity, the luminosity in X-ray of Coro 2 system, right?
Yes.
2A and 2B.
Yes.
And this is a fascinating system. It has been bugging us for a long time.
Yes.
But up until your measurement, so you favor an older age.
Well, it seems like it, right? I know the Corot one is actually a tricky one, right? Because we also have some indications that Corot A might generally be like genuinely
It's
young,
spinning super
right?
fast. It has lithium.
I know,
the planet is super inflated. It can't be
Absolutely.
young. So how can you?
Yeah, it's very tricky, right? Because we have that M dwarf in the system as well, which is really X-ray faint, and it is it is a really mind-boggling system, basically, because how can that M dwarf be so faint if the system is really that young? I'm leaning towards it's old and it's maybe the planet, but I don't have a good explanation for the lithium, and I agree it is a very, very puzzling system. Yeah.
My question was,
Thank you.
And we know that Chaz Beichman, Caltech, JPL, we know that Jupiter is a very strong source of radio emission due to its own magnetosphere. What are the prospects or current status of any radio searches, particularly as you have highly eccentric planets coming in, interacting with the solar or stellar magnetosphere?
Yes. So I'm aware that there are a few groups trying to detect radio emission from such systems. And as far as I know, no unambiguous detection so far has been made. There was a recent paper, maybe like 2 years ago or so, where people observed, tried to detect the radio emission at the planetary eclipse so that you could see the dip. And I think in one of their observations they saw something dipping, and in the next eclipse they didn't, which was very frustrating. But so there are efforts being made in that direction, but I'm not aware of any unambiguous detections yet.
Okay. One in the back, and then we have a gentleman over here.
Joachim Sauer, University of Cologne. Great talk. I'm another red spot.
Can you wave? I don't. Thank you very much.
Another red spot on your map. My question is it clear where in the star the tidal dissipation occurs?
No, I think this is quite complicated, actually. So I don't do a lot of theory, but whenever I talk to theorists, this is quite complicated and not quite clear. What I'm doing as an observer is I'm waving my hands around a little, to be honest here. We know that something is happening when your planet is going around more quickly, but where this is happening, and especially what's happening with the tachocline and stuff like that, so this is something that sometimes gets thrown around when we see this anomalously low activity as well. I think it's theoretically at the moment not quite clear, and with the data I have, I can't make a prediction about that, unfortunately, right now.
Now, actually, because Stefan Mattis is working on that, there are two tides, and you mentioned it. So there is the equilibrium tide that you mentioned, but there is what we call the dynamical tide. And the dynamical tide is dissipated through gravity waves, and it depends, of course, of the structure, if you have a shear layer or not, like the tachocline. But so most of the gravity waves are actually dissipated in the convection zone
This is
of
a
the
comment.
stars.
This is not a question.
No, it was just to comment.
It's a comment. This is not a question. Sir.
Okay. I'm Hervé Bust from the Grenoble Observatory in France. You gave us a few examples of age stars that have that seems to be overspinning with respect to what should be expected due to their age. Well, you told us that this could be due to tidal interaction, even engulfment of hot Jupiters. But I guess that using basic angular momentum conservation, you should be able to estimate a minimum mass of the planets that should be engulfed, supposing they are starting from core-rotation radius.
Right.
And did you do this? And does it turn to reasonable amount?
So I have done this actually as an estimate for a few of these systems actually. And the angular momentum that you get by, for example, moving in a hot Jupiter from, say, 8 days to 4 days or something like that, is actually enough angular momentum to spin up your star by like a delta of minus a few days in rotation period. The angular momentum budget is actually there, and that part makes sense, even before we start worrying about the actual tides or something like that,
Okay.
Okay, I think we are finished here. Thank you. Let's thank our speaker again.